Hello engineers, welcome back to another video. This is the second part of the ROS Learning Series. Before starting with the video, I would like to tell that I will be taking a live class or session on Python for AI on 22nd April this week, Friday. More details about this session and the registration link will be in the description box below. You can attend the session free of cost and there are no prerequisites to attending this session. We will discuss what is AI, artificial intelligence, what are the different AI algorithms, and we will also be implementing a simple AI algorithm in Python. Everything will be explained from scratch, all the AI algorithms and the implementation or the code that we are going to write. So I hope that you register for the session and I will be seeing you in the live class. So now let's go on with the video.
Yeah, before starting, I'd like to communicate about the things we mentioned in the classroom today. First thing is about the assignments. So we received concerns about people refraining from posting into their social media accounts. I think that's completely fine. But the benefit of posting it in your LinkedIn network is that your network gets notified that, okay, you're doing projects in ROS, you're learning about ROS. So what happens is that it will be opening up opportunities for you. So like if some other guy is doing a ROS project, he might invite you to collaborate with him. Also, it can help you to connect with different professors and other hiring managers. So what happens is that when your network gets notified about what you are doing, so it opens up new opportunities for you. So that's the first point. And coming about to the assignment deadlines, so yeah, they are flexible, but please try to complete the previous session works before the next session so that you can catch up what is being taught in the next session. So like today we're going to simulate a TurtleBot. So if you haven't installed ROS, so you might find a bit losing out in today's session. So we would request you to complete the assignments or complete the steps in the previous session before attending the next session. And coming to the certificate of completion, as mentioned, we'll be having two types of certificates, one through attendance and the other through the if someone is posting and is being active in the community. So two types of certificates that we earlier mentioned in the classroom. So yeah, so today first 30 minutes would be giving on the doubt clearing about the installation of ROS. And after that, we'll be starting about the simulation of the TurtleBot. I think Sakshay, you can start.
Okay, so hello everyone. So first we are going to start with the doubt session, and if you had some doubts regarding installing ROS, you can mention them in the chat section over here. So we will go through them one by one. Okay, so the first comment that I can see is that sir, it is saying that WSL2 installation is incomplete and it is not proceeding forward. Let me share the screen first. Okay, so for that, WSL2 installation, while you were installing the Docker, did you check both these options? Like these two options are required so that WSL2 is automatically installed in your system. Okay, so you did check it. So for this resolution, I would like you would have to install the WSL2 then independently of the Docker software. You can do that by going. You can just simply do that by. Yeah, as Rohan also mentions over here, yeah, you just have to download the WSL2 kernel separately to solve this. So you can like it's not like very difficult thing to do. You can just type and install WSL2 and you would get the instructions to just install it. Like there are tutorials available on the internet to do this. So you can like do this. It's not very difficult to do it as such. Hope this clears it. And we have the second, sir. Is it possible for you to give some brief idea of second? So yeah, as Robotics Club commented over here, only one session has happened till now. The second will happen today after the doubt. Also, there is one another thing that we can discuss as well. Like if some people are not able, like there were some comments in the Google Classroom as well that people were not able to install the Docker ROS as their computers were getting slow. So one another alternative that you can try is that this is the you can use the construct. So how would you go about using it? You can just Google this, the construct sim, and this would give you the first link. You can go to the first link and then click on login over here. And after login, it will, okay, so it directly logged me in, but for people who are new, it will ask either to log in through the email, through Gmail, or I think there is one more social media option as such. So you can select that. After opening the this window, we are going to go to this my ROSjects, this left tab over here, and to then we are going to create a new ROSject over here. We're going to click that, and then first we need to select the ROS distribution. We should select ROS Noetic since these live sessions we are using ROS Noetic. So we will select ROS Noetic. We will set any name, let's say demo, and making it private is a paid option, so we have to keep it public, and since we are learning, there is not much of a big deal to keep it as such. Description, you can add any description. We will just go with description and then click create. So on creating, we are going to have the project over here. We have to click it and then click run over here. So it will run, and it is going to take some time to run. And since till it is loading, we can clear other doubts as such. And Hitesh says, sir, is 8 to 12 GB RAM enough with 2.5 gigahertz? Yes, like the RAM, I don't feel that I had, like, even when I tested Docker, I had a very minimal computer as well during earlier days as well. On that, Docker was also working fine. One problem that I most often face with Docker is that the memory, or the main memory that we have, that fills up really quickly. But if we maintain the Docker images, like removing the images that we don't use and removing the containers that we don't use, then it's all fine. There is just a memory issue, the main memory issue, that it takes a lot of space on your computer, but that is a issue that you can also deal with as such. So Hannah asks, is it okay to install ROS on Ubuntu without much virtual machine? Like we install ROS on Ubuntu as such. The thing that we are running on a virtual machine is the Ubuntu operating system. So if you want to install the Ubuntu operating system like dual boot or directly installing it, that is also fine. The method that I discussed in the first session was just for just a easy method to get started, and we do not would have to delve into a lot of installation procedures as such. So that was the reason. If you people can work on a virtual machine, or you can want to dual boot Ubuntu, that is also fine. Then you have to follow the ROS installation instructions to install ROS. That's and yeah, robotics club time. Yes, it's okay. Okay, so Rohan asks, sir, can you also suggest some YouTube channels or some other platforms so we can learn about? Yes. So I'll type it over here. The construct is the, like, I would say it is the best channel that you can have on YouTube. They post content specifically related to ROS, and this the app that we are using right now over here is also built by them. So like they are the experts, I would say, on this ROS thing. Okay, so we have this open over here. So as we can see in the bottom left tab, if you can see over here, we are going to click this shell one. Like this is the terminal. This is the option to open the terminal. The right one is to open the code editor, and the rest for now we can like leave them as such. So if we click the terminal, and then we can see that we open the terminal over here. Now this is very similar to the Ubuntu environment that we have. So we can directly, like we can also code over there. The code editor is being loaded over here. We can type in the instructions for the ROS that we had discussed. Let's type in one and see if, how that works. This was the command that we discussed previously as well. ROS launch gazebo ROS empty world.launch. So now when we ran the command, the gazebo window automatically opened, and after loading, it will automatically open the simulator that we have. So it will take some time to load. And as we can see, we have the same simulation window that we had before. We can also do the same for RBase as well if you want. That is also like almost the same. A window will automatically open. So if we just close it, and then we can close it as well. And for the code, we can type in the, this is just similar to if you have, people have used the Visual Studio Code, it's a similar interface to that. Like we can put code over here. These are the workspaces. We are going to discuss workspaces in today's session, so don't worry much about it. There are different workspaces, different code related files, and we can add all the files over here. Like if you want to create a new folder, we can just type in your new folder. So that's simple as that. It's a little bit slow because I'm running a lot of systems on my computer right now. Otherwise, if you would use it, it's quite decent. Like we can use it to learn ROS, but not for like big development projects as such. Useful, good for learning ROS. Right. Okay. So if you have any more questions. And I hope everyone would have like given a try to install ROS. If it like if you faced any error, then it's like you people have asked as well, so you can ask more questions if you have any such. It's important to install ROS since the installation is the first step to get started with ROS. The next sessions are going to build up over that. We are going to run different robot simulations on the installation of ROS that we have. So if you haven't done this already, you can try it after today's sessions as well. So you can try both the instructions, Pallav. So Ali asks, is this a alternative for Docker, which is better construct sim or Docker? I would say like the reason that why I want to follow Docker with this tutorial is that we would be able to learn about Linux and ROS side by side over here. Like we would be able to see how to work with ROS in a more realistic environment. The construct sim is a tool that is used to teach ROS to students. So the different interfaces, they are very user friendly as such, so we don't have to go through much trouble to deal with the issues. The thing about ROS is that ROS is actually an open source software. Now the thing with open source software is that it's available to all the people to use, and there may or may not be like good tutorials available to it for it to use. So that is one thing. Therefore, the thing that we need to learn is not to just use ROS, but we also need to learn how to use any open source software. That is the main point. If we just use construct sim, then we have everything provided to us. Then we won't have to like go through all the different steps as such. If we use Ubuntu and a similar environment to Ubuntu, then we would also learn how to use any other open source software that we want to use, not just ROS. So that's the thing. Also, the different ROS packages that we use, they are also like it's not necessary that the tutorials for all the ROS packages will be available on the internet as such. There would be some ROS packages that we have to build ourselves, or some ROS packages whose tutorials would not be provided. So we need to learn to use them as well. So that's why we are following this Ubuntu based approach, the Docker one, rather than the construction. Uh, Also, one more thing, since we are discussing and there are no questions as such, like in the slides over here, I think I did mention this, that yeah, we like in the posts also, that I saw that the people usually ran the empty world gazebo over here, that we also saw in the session also. In the slides, I also mentioned that we can also try different worlds also, like the elevator world, empty world, mud world, and so on. So in the empty world, we are only seeing empty space as such, but in the other worlds, we can also see some other environment as well. Like in the rubble world, there will be a lot of like rubble based things that are present in the environment. Mud world is like a mud floor would be there in the environment. So you can also try these out, like, but if you like, today we would also go over TurtleBot 3, so you should like first try that out, and if you get time, then you can try this out as well. That is also.
Since there are no more questions, I think we can start with today's session.
Okay. Okay, so let us start with today's session. Hello, engineers. Welcome to the ROS Learning Series. This is part 2 of the ROS Learning Series. In today's session, we are going to simulate the main agenda for this for today's session is to simulate the TurtleBot 3 robot. So let's get started with that. So brief recap what we did in the previous session. In the previous session, we discussed the installation of ROS, like how should we install ROS on our system. We mainly discussed a Docker-based approach to install ROS. This was done because we want to, it's the most easiest approach that I feel that we can use to install ROS, like the minimal installation instructions that we have to follow. So that's why we use the Docker one. And I hope that all of you guys have tried installing ROS and have a ROS system that is on your computer. If you do not have it, you can try this after this session as well, and to try today's tutorial instructions as well. Okay. So let's first briefly talk about the TurtleBot 3 robot. So the TurtleBot 3 robot is a educational robot that is used to teach robotics to students. And as we can see, there are different variants of the TurtleBot3 robot. Like we have a TurtleBot3 burger, TurtleBot3 waffle pie. All of their shapes are different. And also one thing that I would like to mention, that it is a physical robot that we can buy. Right now we will only be working with the simulation, but if you would like, it's a bit expensive over here in India, I believe. Like for students, its price range is quite high. Hence, we are not going to be using a physical TurtleBot3 robot to learn the robotic stuff. We are only going to use the simulation. So also the TurtleBot3, it's actually the third generation robot of the TurtleBot series robots. Currently, the TurtleBot 4 robot is also under development, and it will be released, I think, pretty soon. For the time being, we are only going to use TurtleBot 3 robot. Okay, so one question that I would like to ask, like you just have to take a guess. Any guesses why this robot is actually called the TurtleBot robot? Any guesses for that? Because it's slow. It moves slow. Okay, so I would provide a hint as well. It's related to a programming language that was, I think, taught to us when we were kids. Like when we were learning computers, it was a programming language that was taught to us to draw shapes. Okay, so Kritika and Anish are right. It's the MS logo. So what was there in the logo? Yes, Aishwarya also said logo. Everyone says logo now. So logo was actually a programming language that was used to teach students programming. In that, we had to like draw the different shapes by providing programming instructions. And the cursor that we used over there, the cursor that drew all the shapes, was called turtle. Since turtle was used to teach students programming, TurtleBot is used to teach students robotics. So that's where the name comes from. Apart from that, now in the physical robot, we have the battery component. As we can see, we have the different motors, the tires, the computer system, and even the CPU as well. One key thing that all these things are present, but one key thing that I would like to note is that it has a device called a LiDAR. Now, LiDAR is an important hardware in robotics. Like it is used by a lot of different robot applications. Particularly for our case, we are going to use the LiDAR for localization and mapping. Now, these terms may sound a bit unfamiliar to you people if you are new to robotics, but we are going to discuss them towards as we go through the session over here. Okay, so first let us discuss what is a LiDAR. So LiDAR is a device. It is a laser-based device that is used to create what are called point clouds. As we can see in the animation over here, that a laser is emitted by this LiDAR device, and this laser is then just goes to the environment, reflects back, and through that reflecting back, the LiDAR is able to detect the distance at which the point is. As we can see over here, this 2D environment is being mapped by the LiDAR sensor over here. Like we can see the different points that are mapped to that. LiDAR can also be used to create 3D point clouds as well. This is just a 2D working. If we rotate the laser in other rotation axis as well, then we can get a 3D point cloud as well. Yeah. Now, okay. So again, one more question. Can anyone guess which car is this? Like the logo is quite, I think, clear, so you can guess which car would it be. Yes, so it's a Tesla. It's Tesla model Roadster. Now, why did I put this picture over here of the Tesla car is that almost all the self-driving companies, that the current self-driving companies that we have, like Waymo, like Mercedes-Benz, and so on, all of these companies in their self-driving car, they usually include a LiDAR sensor in their self-driving cars. All of the companies except Tesla does not do this. They have their system, the self-driving car software. It does not depend on LiDAR at all. All of their complete system is just dependent on camera sensors. The reason why Tesla does this, and Elon Musk also says this, that humans only depend on their eyes while driving. There is no hardware that is attached to humans, that is like LiDAR that sends out laser and calculates the distance. It's only the vision system that is used to drive a car. Hence, we to uh, behave similar to nature, the Tesla car company does not use LiDARs at all. Hence, they only rely on the vision systems. One more drawback that we have for LiDAR, and what makes it difficult for beginners to get started with hardware ROS as well, is that LiDARs are quite expensive hardware. So it's quite expensive to get a hardware. So these two reasons combined, Tesla doesn't use their LiDAR systems on their cars. But LiDAR is an important a component of robotics, hence we should be learning about it. This was just a small trivia fact that just wanted to discuss. Okay, so I mentioned two terms before that were mapping and localization. We are going to discuss three terms over here, which are mapping, localization, and navigation. Now, these three are actually components of a big robot as such. Now, just like we discussed in the previous session also, that there are different components of a robot. When we are building a robot, there may be a vision system, there may be an audio system, there may be a motion planning system, and so on. These three terms that I have mentioned, they are also components of a robot system. A robot has to do mapping, a robot has to do localization, and a robot has to do navigation. Now, these three terms are completely related to the mobile robots, like the TurtleBot3 that we discussed. The wheeled robots, mostly mapping, localization, and navigation are related to these mobile robots. So let's understand what mapping, localization, and navigation are. So imagine that we have gone to a vacation. So we have reserved a hotel, and now this is a quite this would be quite possible that you are going to stay in that hotel for the first time. Now, when we go to the reception and we are allotted a room and we go towards our room, we have not seen the hotel at all. It's the first time that we are seeing that hotel. So what our mind does, you would have noticed as well, what our mind does is that it creates automatically a map of the complete hotel environment. In the rooms that we go and the hallways that we follow, our mind automatically creates maps of the observations that we took, like the door is over here and the turn is over here and so on. Now, this process in which we create a map of the environment is called mapping. Mapping is simply creating a map of the environment when we see it for the first time or for some other time as well when we are exploring the environment. Now the next task, let's say that we are at our room and we now want to go to the reception. So in our mind, we would automatically plan a path, like first we need to go out of this room, then we need to turn left, then we need to go straight, and then we need to go right. We would create some kind of plan like this, and then we would try and follow that as well. Now this creating a plan and then following it is what constitutes the component navigation. Navigation is responsible for moving us or planning the path that we want to take to go from one place to the other place. Okay, so for the planning, now there is one quite prerequisite that we need to consider for planning. Our plans would only work if we know where we are currently in the map. Now, if we are in the room, then our anchor point or starting point for navigation is the room itself. If we are at any, like, let's say we are on the path to the reception, so that now our anchor point is at that point. So our planning would work like, our planning only works if we know the initial position of ourselves on the map that we have built. And this system of knowing the position at which we are currently on in the map is what's called localization. Now, there's also a curious question that you would ask, like we would also need localization for mapping as well. Like when we are creating a map, we need to know where we are in the map so that we can efficiently create the map of the environment. Now, this is a well-known problem in robotics as well. Like, should we first localize on the environment, or should we first create a map and then localize, and like so on? So this simultaneously doing this localization part, telling ourselves where we are on the map, and this mapping part, creating the map as well, this constitutes what is called the SLAM component. SLAM stands for simultaneous localization and mapping. So here now, as a quick recap, now we have four components of a robot system, which are localization, mapping, navigation, and SLAM, simultaneous localization and mapping. So these are the four basic components that build what is a mobile robot. A mobile robot, well, if we want to build a mobile robot, let's say from scratch, a wheeled robot, then these four components are very important for that wheeled robot. Based on our task, there are certain extensions to the that we can apply to the robot as well. But these are the four basic tasks or core components of a mobile robot as such. And okay. So these are some simple animations to just see, to visualize these things. The things that the components that we discussed were in terms of human brains. So these are just some visualizations to see the components in the robot kind of environment. So as we can see, the robot, as it is moving around, it is creating its map. And not only it's creating its map, it is also localizing itself on the map as well. Like the robot knows where it is while it is creating the map as it moves across. So this is the localization mapping part. Next is the localization and the navigation part. Now, if we see these red dots over here that we see, now the robot is at the start doesn't know where it is. So it created initial guesses in the form of red dots that we saw. Once the robot moved a bit around, like if we will discuss this after this animation starts again. Like this is the navigation part that is going on currently over here. The robot is navigating from part A to part B. Let's just wait for the animation to begin again so we can discuss the localization. Okay, so now initially the robot does not know where it is. Like in the start, it is believing that it is over here. And there are different predictions where the robot would be. As the robot moves around, it is predicting where it should be on the map. So once it knows where it is on the map, then we can do the navigation part. So once the robot knew where it is, it sent the goal to the robot and then it started following the path that it created. So localization and navigation, like they both go in hand as well, as we saw. Okay, so before going on any further, are there any questions or doubts related to these four components as such? Like we do not need to know the exact algorithm that goes behind these localization, mapping, and navigation. ROS will automatically take care of them. We just need to know that these type of components exist in a robot system. That's all. Okay, so no questions. So okay, in positioning, is relative positioning being used or absolute? So the question that Rohan asks is, in positioning, is relative positioning being used or absolute? It will, I think relative positioning is not used. Like absolute positioning is used. First there is a coordinate system is set where we want to set the origin of the complete system. Once it is set, then we localize our robot based on that. Now, relative positioning would also I would say that absolute positioning is used as such. Relative positioning is also like, if we know the origin of the absolute location, only then we can derive the relative positioning over there. So that's kind of the thing. There is the first step in any robot system that we have to do is set the coordinate axis. First, we set the origin of the complete system. Then we set a coordinate axis on the robot. Now, based on both of these, then the localization algorithm works like based on the robot, what the robot is seeing in its relative environment, how does it look like in the absolute environment? And it does some kind of mapping like this to create a complete map of the environment and localize it itself as well. Okay, so moving forward, okay, can you repeat those terms, which four components you mentioned? So first is the localization, second is the mapping, third is the navigation, and fourth is SLAM. SLAM stands for simultaneous localization and mapping. I would say that the three components are the main. The fourth is just a derived thing of the complete problem as such. So these, I would say, three components are the main: localization, mapping, and navigation. The fourth one is just an extension of the previous components as such. Okay, so moving forward, now, as we discussed in the previous session as well, that a person working on robotics, if they are using ROS, then they do not need to worry about the implementations of the different algorithms. Now, these components that we discussed, localization, mapping, navigation, and SLAM, these are research areas on their own. Like people research on the algorithms for these components, and after the serious research that goes on, algorithms are developed that actually solve these kind of components. So we cannot, as a roboticist, we cannot go on implement all the different methods and compare which is working best or so on. ROS provides us with the all the different components, the different algorithms that we can use directly without their implementation. Hence, there are ROS packages that are available for localization. For the four components that we discussed, we have different ROS packages. Now, since these three or four components form the basis of, or the most fundamental components of a mobile or autonomous robot, hence ROS, we can individually download the ROS packages for them as well. But ROS provides us with a collection of these packages, which is called the ROS navigation stack. If we type in install ROS navigation stack, it will automatically install all the ROS packages that are related to these four components that we discussed. So we can understand that ROS has a dedicated like stack for all this. So how important it would be for the mobile robotic stuff. Okay, so this is all the theory that we had. Now let us simulate the TurtleBot 3. And yeah, before, since like, okay, so if there are any questions, they can ask as well. We will just go on to simulate the TurtleBot3 robot. Okay, since we are using Docker as such, and if you're using other system, then the starting would be different. So as we discussed in the previous session as well, if you want to again use the Docker container that we built in the previous session, then you would need to click the start button over here. I have already started the ROS container and it is running. We have the ROS tutorial over here and it's already running, right? Also, the installation steps that we are going to discuss, everything is same, that you have to replicate the instructions and put a post on social media that describes how you did the complete thing. And all the steps are also present in the slides, so you can focus just on the part that we are doing, and we can you can later refer these slides to follow the instructions. Right, so we have to go to the 127.0.0.1 6080. Okay, so I'll also refer the steps since I don't also remember this. Okay, so the first thing that we need to do is open the terminal. As we discussed previously as well, we can go over in the bottom left button and click that, go to system tools and then click LX terminal. It is going to open the terminal. I'll increase the size so we can see. The first step that we need to do is type this command sudo apt get update. This is simply to when we are running this Docker environment, then we have to first update the different links from where installation is going to occur. Do not worry about it if you do not understand it. It's just a general step that we have to follow while we are working with Ubuntu. When we want to install the different packages, this is like the first step that we have to do: sudo apt-get update. Now I'm not going to run this since this requires internet. So the instructions given over here would require some time that it will take on its own, depending on your internet connection. So I'm not sure about my internet connection in these moments as such when I'm doing a live session. So I will not run this command. You have to run this command so that you can follow up with the other commands. Okay, once you have run this, okay, I'll just run this and then cancel it to just okay, so it will just like run on and it will take its time. The next step that we have to do is install the ROS navigation stack. So the command for that is sudo apt-get install ROS noetic navigation. This is once again going to install the components from the internet. Since I do not trust my internet connection, I will run this command and then cancel it. It will take its time as such. So that's the next step. Okay, so in the doubt session as well, what we discussed that we want to learn not only how to use ROS, but also how to use any online, any open source software. So how do you use open source software is that you need to Google everything. So the process that I'm going to discuss over here is completely raw. I'm not going to give the direct instructions how to install TurtleBot3 and how to get it running. That would be very simple. We are going to discuss what is the most raw form of how we would go about simulating any robot as such. For our case, now simulating TurtleBot3 is the easiest because the tutorials are available offline. Hence, we are going to see how do we need to follow those tutorials to install the TurtleBot3 robot. So first we need to go to Google and then we need to just type in TurtleBot3 simulation ROS. It will automatically give all the results. And the first link is that we have to go. This is the official tutorials for running TurtleBot3 simulation. So once we are on this step, we are going to go to this left pane over here that says simulation and click on it. And then we need to go over this gazebo simulation over here. So we are already on this page and we want to select noetic over here as we want to see the instructions for ROS noetic. So as we are over here, this is the first step that they have given that. Now, if we read it carefully, they say that the TurtleBot3 simulation package requires TurtleBot3 and TurtleBot3 messages packages as a prerequisite. So we need to keep this in mind. And so before beginning with this installation instructions, we first need to install the TurtleBot3 and the TurtleBot3 messages packages. Okay, so the thing that we have to do first is that before installing any ROS package on our system, the first step we would need to go to the desktop, CD desktop, and we want to create a new directory that goes by the name of Catkin workspace. I'll just type the command over here. Now, what this mkdir-p Catkin workspace means is that we are going to create a Catkin workspace directory and we are going to have a src folder inside of it. I'm just going to, since I already have this Catkin workspace over here, I will just change the name slightly so we can see how it actually looks. So we run this command and we can see we have this Catkin1 workspace. If we open it, we have a folder inside it, src, and that is empty. Now, all the ROS packages that we are going to install are going to go inside this src directory. That's the main thing that we wanted to note. Now, what this Catkin workspace is, like if you have people worked with C++, then you may know how that we have to first compile the code and then only we can run the C++ code that we have. In big software like ROS packages, these are big complicated software mechanics. Over there are a lot of different files that we have to compile. We have to compile different libraries and the instructions for that are just quite big and quite different for the different ROS packages. What Catkin workspace will do, it will automatically build all the packages for us. So we do not need to type in manual commands to build the C++ files. That's the advantage that Catkin workspace provides us. Okay, so we are going to first go to catkin workspace slash src. In this folder, we are going to clone all the ROS packages that we have. Okay, so as they say, we require TurtleBot and TurtleBot3 messages packages as a prerequisite. So we are just simply going to Google this. How should we go about installing it? Okay, so first we will type in. Okay, so the thing that we're going to type over here is TurtleBot3 ROS package, and then we're going to type GitHub. Now the first link over here is the one that leads us to it. So you click that. Okay, and this is the TurtleBot3 ROS package repository. Now, if you're people not familiar with GitHub, GitHub is a website where people upload their open source software. We also, us students as well, can upload the open source software, and big companies also can upload their software over here as well. So since ROS packages are open source software, they are present on GitHub, and we can install them on GitHub from GitHub itself. Now, the key thing to download this is that first we need to click this code button, and then we need to copy this link. This link is going to help us to download the ROS package. We copy this link by clicking this button over here. Then we go to no VNC. Now, if you are running this on a native Ubuntu installation, then you can simply type Control V or Control Shift V to paste over here. For the Docker version, what we need to do is click on this small right arrow over here, click on this clipboard, and then paste the link that we have in this clipboard. Now in this clipboard, when we Control V in the terminal in the Ubuntu, then it's automatically going to paste. So it's just a small thing. So the command that we're going to type is git clone -noetic devel and the link that we have. You can see, I'll just close this. This is the command that we use to download any repository from GitHub. Now, why I typed this -b noetic devel, it is to install the noetic version of ROS of the ROS package. It's just simply that. So we'll just press enter, and it will automatically start installing the TurtleBot3 package. Once again, this is going to take some time based on your internet connection. Hence, I have already have them installed in my src directory. I'll just show it to you. So we have this TurtleBot3 already installed. Next, we need to install the TurtleBot3 messages that they mentioned. So we are going to just type in _messages. And then we have this link. Yeah, we have this link over here. This third one. And we're going to TurtleBot3 messages. And then simply we can just copy this link and do the same command for that. The simple difference I would say is this: we just need to type _messages and it will install that as well. So we are now done with the prerequisites. Now let us see what are the actual instructions. I'll just zoom in. Okay. So as we can see, the first command is to git clone the TurtleBot3 simulations package. Just like we installed TurtleBot3 and TurtleBot3 messages, we have to clone this TurtleBot3 simulations as well. This is exactly the same that we have to do. And after doing that, we would have something like this: TurtleBot3 simulations, TurtleBot3 messages, and TurtleBot3. Now, once we have these different repositories installed on our system, the next step that they say is to go to the catkin workspace and type in catkin make. So catkin make is the command that is going to install all the ROS packages. So we're going to go to catkin workspace by cd .. and then type catkin make. Now this is not going to use internet at all. Hence it will run quite quickly compared to it will depend on your system configuration. If you have 4 CPUs, then it will run faster. If you have 8 CPUs, then it will run even faster than that. So this depends on your computer system, not on the internet. Next step that they say is, now the next step that we're going to run is the empty world. So they say first we have to type in export TurtleBot3 model and then use this ROS launch command. Before running these commands, we need to type first this command source devel /setup.bash. What it will do, it will tell the computer to load the different ROS packages. Once we have ran the catkin make command, it has only built the ROS packages. But in order for the computer to know where the ROS packages are located, we need to type this source devel / setup.bash. This is an important command that we always need to run before running any ROS package or ROS workspace. This is the first command that we should be running, and we will be running it in following as well. So the first command that they say is we need to set the TurtleBot3 model, which we are going to set over here. Let's just set it to worker, right? And then that command is TurtleBot3 gazebo TurtleBot3 empty world.launch. So one trick that I would like to tell, now we do not have to write this complete ROS package name. What we can do is simply type in the starting initial. Once we have typed this, we then press the tab key on our keyboard. It will auto complete the rest of the package name as such. So now we are first going to type in TurtleBot3E, and this then typing in tab will automatically complete the empty world.launch. Now let's run this ROS launch command and see how the robot is simulated. So as we can see over here, we have a TurtleBot3 robot simulated in Gazebo. On my system, it is slow because I'm once again running the Google Meet as well. On your system, it will be comparatively faster. Okay. Now simulating the robot is just a very trivial thing. It's like what we will do after simulating the robot. We need to move the robot as well. So let's see the instructions to move the robot. If we scroll down, then they have this command over here, operating TurtleBot3. For this, they simply say that in a new terminal window, if we read it carefully, they say in a new terminal window, ROS launch TurtleBot3 teleop TurtleBot3 teleop key.launch. So we are going to run this command like this. We will open a new tab over here. So the first step that we discussed was to run the source devel setup.bash. Otherwise, it will not work. Also, in these instructions, it is not stated, but we also have to run this TurtleBot3 model command as well every time we launch a new terminal, and it has to be the same that we set in the previous terminal. Once these two commands are set, then we can type in the command that they have given. So now we have this ROS launch command running. As we can see, they have given the instructions how we have to move the robot. W will move the robot forward, A to the rotate it to the left, D will rotate it to the right, S will stop it, and X will make it go backward. So let's run this, focusing on the terminal. And as we can see, as we increase the speed, it is going forward. Now I want to stop it, so I will type in the S. S will simply stop it. Now to rotate it, I will type in the key A. It will rotate the robot. To stop it, S. Rotating it to the right by pressing D. So it will rotate it again, and pressing S will stop it. So these are the basic commands to get started with a TurtleBot3 simulation in an empty world. So like this is the phase one of the complete demonstration that I have. Now, if you have any questions regarding this, you can ask the same as well. After these questions, we are going to move into the next section, which is the SNAM simulation. Now, one thing that I would like to note is that this demo that we're discussing today is a bit elaborate. So you can take your time while trying it. It is a bit elaborate. We have 3 components that we want to discuss today. So you can take your time while you're doing this on your own as well. Okay, so we don't have any questions, so we will move forward. Let's just close this and close this as well by typing in Control-C. Over here as well, Control-C. Will take its time for the time being. So the instructions that they say is that first we have to ROS launch TurtleBot3 gazebo TurtleBot3 world.launch. Then we have to run the slam node in a new terminal that by command turtlebot3 slam, turtlebot3 slam dot launch and slam methods g mapping. Then we have to run the teleoperation node. Now what slam is, that like we discussed, we are going to create a map of the environment using this slam environment, slam simulation. We need to create the map of the map of the environment. So it's closed. We will run this again. This time it's TurtleBot3 world.launch. Okay, so we have this simulation over here. This is the environment that we have, and where we have a robot, small robot over here. Okay, so just minimize it. And in the next, in the other terminal, they say that we have to start the slam node. For that, the command is ROS launch turtlebot3 slam, turtlebot3 slam dot launch. So let's run this. Now in this terminal, we have already run the source devel slash setup.bash and the export turtlebot3 model command. So we don't need to run them again. We simply type in the given command that we have. Bot3 slam, bot3 slam. Okay, let's run this and we are going to increase the terminal size. Okay, so this is important over here. Now what we can see is that we have an error over here that says cannot launch node of type gmapping slam gmapping gmapping. Now these kind of errors are usually common when we are working with open source software. Since the installation instructions were not clear about this as well also, we do not need, we need to analyze this error and see how we can work on this error. What I can see is that based on this error, this simply means that the gmapping is algorithm or the gmapping ROS package is not installed. So how we are going to install this? We are going to go, just simply we are going to Google this, install ROS package gmapping. And we have this, okay, ROS noetic. Since we are working with ROS noetic also. So we can see that the first link that we get over here simply says we don't even have to open the link. It says sudo apt-get install ROS noetic gmapping. So this is exactly what we are going to run over here. Sudo apt-get install ROS noetic gmapping. Now this is going to take some time based on the internet connection again. But the package is, I think, small in size, so it won't take much time. Now, after you have worked with ROS like pretty much, you would get to know that the basic structure of any ROS package, to install any ROS package, it's just we need to ROS the version and my hyphen the ROS package that we want to install. So it's a general structure. We can even brute force it as well if we want. So now we have the ROS gmapping package installed. Now let's run the command again and see if the error is resolved. Okay, so there is no error over here and the slam gmapping is working fine. So we have this RWiz window open over here. As I said, the robot right now doesn't know how the map looks, what environment it is placed in. Hence, we have this partial map over here. Our task in this slam component is to build the map. So let's see how we're going to build that. First thing, now since we have this RWiz running as well, we can close the gazebo. Now the thing about gazebo is that the gazebo's GUI component and the computation component are different. This over here that we can see is the GUI component. We can, without any worry, simply close this and the computation would still keep on running in this terminal window over here. So it's just a way to save some computation. I'm doing this, as you know, but it's your choice that you want to see the robot in simulation as well. So it's completely your choice. For RWiz, this won't occur. If you close the RWiz window, then it's going to close the software as such. Okay, so we'll just first maximize this. Now, how to build the map is simply to move the robot around in the map to build the map. As we discussed before, how we can do this is to launch that teleop ROS launch and using that we can move the robot around and build a map. So let's do that. First step that we need to do is source dev/setup.bash, and then we need to export the TurtleBot3 model. Then we want to run the teleop launch, as we can see over here. Let's make it a smaller size. Okay, now let's move the robot around and see how the map is being built. I'm moving the robot in the forward direction. As we can see, the map will be slowly, we will be building the map. So slowly the map is being built. All we have to do is, this is just a spoiler, I would say, that in order to build this complete map, we only have to take, first we need to go through this lane, then through this lane, and then through, we have to go through these 4 lanes that we have. By just simply going through these 4 lanes, the map will be built. Now, once we have this map, now we need to save this map as well in order to be useful for the next steps. Let's see how they tell us to do it. They told us to run the teleoperation node to move the robot. Next, they say that to save the map, we simply need to run ROS run map server map saver -f, the location that we want to save. Okay, so for that, we are going to go to new tab. Now, over here, simply typing dev/setup.bash is enough. We do not need to type the export command as well. We're simply going to run the ROS run command that they have given. ROS run map server map saver -f, and they have given ~map. What I have done and what I recommend is that you save this on the desktop over here. Will you type this command as such? This would be better as it would install it on the desktop. But for now, I'll just follow their commands to just show what it is. As we can see, the complete map is now built and it would be saved in this directory over here. Let's go check that. Okay, so in the home folder, we can see that we have this map.pgm and map.yml. These 2 files are saved. If we open the, okay, map.pgm is simply an image file that stores how the map looks, and map.yml contains the information of the map. Now, the task for you is to build the map. When you are running this tutorial, you have to build the complete map and save it. Since I have to save on the session time as well, I have already run it and saved the map over here, map.pgm and map.yml in the desktop. And this is useful because in the next section, that now we are done with this LAMP section over here. In the next section, for the navigation to move the robot from point A to point B, this map is required. Hence, we need to build this map before going on to the next section. You just give it a try. A partial map would also be good, not completely building the complete and good map. Even a partial would also be good, so that almost everything is covered in the map. That's the key thing. Okay, so this is done for the second phase that we had to discuss. We'll just close everything that we had, and now we will move on to the next section. Before that, if there are any questions, you can put them in the chat. The next section is the navigation simulation. Oh, okay. Soumya, the past said, what if we move the bot through all rows in one go? Yes, this is exactly what you have to do. Move the robot in a zigzag kind of way so that the robot goes through all the rows. Saving for every row, you do not have to save it for every row. Just run the robot around the map once. And once you're satisfied with what you have, then finally, you then save the map. That's how you need to do it. Okay, so no question. So we will be finally moving on to the last one. Now, this is the actual place where we would see actual robotics in work. We will be seeing how the robot is moving around the world. Okay, so we are again going to launch. Okay, you have to follow the instructions. Since I have read these instructions quite some time, I think I have memorized them. But you can follow these instructions given and then do the work. Okay, so first we need to run the TurtleBot3 world.launch. And once again, we are going to close the gazebo window to save on some computation, since we do not require it for now. I'm going to simply close it and it will keep on running in the background. Okay, the next command that they say is ROS launch TurtleBot3 navigation, TurtleBot3 navigation.launch, and we need to specify the map file that we saved, $home/map.yml. Now let's run this command. Okay, so $home is simply a $home is simply a shortcut, we can say, for tilde. Now what the problem over here is that we cannot type the tilde command over here. It does not read it. Hence we simply use the $home. And then we go to /desktop and /map.yml as they have given. Let's run this. So we have this over here. Let's maximize the window. Now over here, the thing is that the robot does not know where it is on the map. As us humans, we knew that the robot was over here, but the robot itself at the start doesn't know where it is. We need to localize the robot. So the next step that we need to do, first we will do is that we need to run the teleoperation node again. Since we want to know where the robot is, the robot has to move around to see the environment and determine where it is. Okay, so the first thing that we do is click over here, this 2D pose estimate. This is just an estimation of the initial location. It can be anything, like there can be some error when we put it over here, but it has to be slightly correct. So we will click on it and drag in whichever direction the robot is facing. We can be slightly wrong in this. There is no problem as such. So when we set the initial estimate now goes over here. Now to actually localize the robot, we just need to move it around. Spoiler alert again, we will simply move it forward and the robot will know where it is. So let's see. Moving the robot in forward direction, and we will soon see that these green dots over here, they will localize to a specific location where the robot is present. Right now they're completely random, but as we move it, the robot in front forward, these will converge to a single position. Not all of them, well they will converge, but not all of them will point at the same position. They will just be in a circle over here, as we can see. So this is the much that we can get. The robot has been localized, that it is somewhat present over here. Now to run the navigation, we select the 2D nav goal button over here. We click on that, and then we click and drag the robot, the arrow that at which point we want the robot and which position we want the angle we want the robot to face in. So let's say we want to move the robot over here and we want to keep the direction over here. So we set this, and the robot will then automatically plan its path and move towards the goal. So it will slowly move towards its goal. And it may also happen that the robot may get stuck. For that, it's just a general issue that I have seen. It's not much of a big deal. We can set a new nav goal and then the robot will start following that. So that's not a big deal. It happens like the robot is stuck somewhere as such. Well, as I discussed, so I think the robot is stuck, I think. As we can see that that the robot is not able to decide whether it should go forward or backward. So we will just set a new goal to just demonstrate that. It's again stuck. Okay, we'll just set it over here then. Okay, putting it in a straight way, it seems to be working. So this robot will just follow the path that it has. In the simulation, we will also see that the robot is following the path and moving to follow that in the simulation as well. So in the RVs, we can also see this. No, it's probably a bit slow because of my system. Otherwise, you can try this on your system and you would see that the robot would move towards its goal. Right. Yeah, it's slowly moving. So, yeah. All right. So I think this is it that we had to discuss. Like you can see, the complete instructions are given in these webs in this website. As we can see, the robot moves along. Okay, so this is all that we had to discuss. If you now have any questions related to everything in the session, you can ask, and that's it that we had to discuss. Also, just before we go on, I would like to say that so once again, the instructions are still the same, that you have to replicate the instructions that I showed and post them on social media. You can be as creative as you want if you want a video, GIF or images. In the next session is going to get a little bit theoretical. I would say that we are going to discuss about the ROS concepts. From like in the first two sessions, we have only discussed like what is ROS, how to install ROS, and did the TurtleBot3 like simulating it. These are all the cool things that we can see in robotics. But in the next session, it will be, I think, slightly more theory based, that we're going to discuss the ROS concepts and see how things work in ROS. That is the main thing that we want to learn. Simulating robots is one thing, but we also need to know the theory. So that will be discussed in the next session. So we are done for this today's session. If you have any questions, you can ask them in the chat.